Yeah, hello everyone. Nice to see you or like seeing you in the room. So my name is Julia, and it is a great pleasure to welcome all of you to Alexei Efros talk here at AI Helps Ukraine. And a warm welcome to everyone who joined us before, and thank you to everyone who supported us and is key, everyone who keeps supporting us. And for everyone who's here for the first time, you're at the right place. Let us know in the chat if you have any questions or any problems, and we will also tell you a bit more about us in a few moments. So while one or the other are still in the process of joining or trying to maybe find a cozy place to listen to this talk, we would like to tell you a little bit more about AI Helps Ukraine. Name-wise, it will be a little bit confusing today because Alexei number 2 will talk about AI Helps Ukraine. But lucky enough, you also have different nicknames. So I'll go with Alexei, your Ukrainian nickname for today.
Yeah, thanks, Julia. Thanks for introduction. My name is also Alexei, and I'm part of the team that organizes AI Helps Ukraine, and I would like to take some time to briefly introduce you to AI Helps Ukraine, to this conference. So AI Helps Ukraine is a student-led fundraising conference in AI. So the aim is to bring together the leading experts in the field of AI to raise money and to raise funds for humanitarian help for Ukraine. As you might know already, we are hosting a series of online talks throughout the months of November and December. Additionally, we will host a full-day in-person event on the 8th of December here at Mila, and you're all very welcome to join if you're around. So it's been 9 months since the Russian invasion in Ukraine began, and the level of death, destruction, suffering inflicted on the civilian population is beyond any comprehension. And no one in Ukraine is left unaffected by this war. So these are just normal people like you and me who are living their normal lives, bringing kids to school, going to their office to work, meeting their friends in cafes, having their normal lives until the 24th of February of this year. And so within the past 9 months, around 13 million people have been forced to leave their homes. An estimated of 18 million people will need humanitarian aid. And the Ukrainian Ministry of Health estimates that 15 million people will require psychosocial support. More than 15,000 of civilians have been killed or injured. And on the right-hand side, you can see some examples, some pictures from the Kiev region, for example. So the upper picture is, for example, a picture of a district where I personally grew up. And just in front of this bombarded building is a school that many of my friends attended, and the school where I learned to play basketball. And so critical civilian infrastructure is a common target for Russian attacks. Russian army clearly intends to undermine industrial production, disturb transportation, spread fear, and deprive the civilian population of heat, electricity, water as winter approaches. And hundreds of thousands of people lack food, water, heat, electricity, and medical care. And for this reason, we insistently remind you to support our cause through a donation. And this donation will be used to purchase things like the device that is depicted on the left-hand side on the screen. And so this is a negative pressure wand therapy device. And these devices are especially needed for injuries that people get from missiles, which is unfortunately still happening a lot these days. And we would like to especially highlight that it's really not important how much you donate. The only thing that really matters is that you do not become indifferent. And so the biggest power that we think is in unity. And so our team strongly believes that the collective effort of our broad machine learning community, that is international community, can really make the difference. And this difference can become even broader with every retweet or every small donation that you make. And last but not least, we would like to especially thank our partners, which is Mila and Ukrainian Medical Support, a Canadian-based nonprofit organization from Toronto, and one of our first corporate partners, which is Google Montreal. And so with this, I would like to give a word back to Julia, who will introduce our speaker and the house rules.
Yeah, thank you so much, Alexei. So I'll start by quickly introducing our house rules. Everyone is welcome to use the request chat during the presentation for discussion and comments and sharing relevant papers. And you can also use the Q&A feature to ask questions to the speaker for the discussion time after the talk. And you can also just write your questions in the chat and we will put them Q&A. And you can also upvote the questions of others. So we all here strive to make this virtual conference an inclusive and safe space for everyone. And so we kindly ask you, the audience, to help us with this. We have a code of conduct in English and in French, and that is available on our website. And according to it, we want to keep things nice for all. So any hate speech or harmful comments will not be tolerated. And so with this, we can finally introduce today's speakers. Alexei Efros, thank you so much for being here. Surely he does not need a lot of introduction to most of you, thanks to his groundbreaking works in computer vision and in computer graphics. And all of those of us who have worked with self-supervised learning will also know him. And he himself says that the goal of his research is to use vast amounts of unlabeled visual data to understand and model the visual world around us. Since 2013, he has been a professor at the Electrical Engineering and Computer Science Department at UC Berkeley, and he is also part of the Vera Lab at Berkeley. I think many of us know the name and the logo. And before, he spent 9 years at the Robotics Institute at CMU. And he has, of course, received a number of awards, among them, for example, the Guggenheim Fellowship and the Diane McEntry Award for Excellence in Teaching Computer Science. And I think the students in our audience will be happy to hear that he's also an advocate for slow science. And last but not least, we want to mention that Alexei is one of the speakers that is really very close to our hearts because he has been supporting Ukraine openly since the beginning of the invasion. And we are really happy and very honored to have you here today, Alexei.
So yes, Alexei, the floor is yours now.
All right. Well, thank you very much for giving me the opportunity to speak. Let me share my screen. Yes, this I'm very honored to be here, and I like to thank you guys for organizing this. I think this is a fantastic opportunity. You know, when this thing started in February, the worst thing is, you know, we are sitting here in North America, nice and safe, and like you know, every one of us is thinking, what can we do? And I think this is a great way to try to help. So before I start my talk, I think I just want to take a couple of minutes to give my take about why this is so important, especially given that we are so far away, you know, half the world away. And what I hear often, you know, on my campus here in Berkeley is like, well, it's just a regional conflict in some faraway land. And this is absolutely, it's very far from the truth, because in reality, this is an absolutely existential battle between reason, liberalism, and democracy itself against tyranny, oppression, and really the new coming dark age. And this is just the first part of this battle. And this things are really very serious. The stakes are absolutely enormous. I think the stakes are even more enormous than during World War II. It's really that serious. It is probably one of the biggest challenges that our world has ever faced. And it's not that, okay, you know, Putin will take Ukraine and that's it. No. I was born in Russia, and I can tell you, Putin's goal is world conquest. He will not stop unless we stop him, but he must be stopped. And the thing is that right now, only one country, it's the Ukrainians, who are fighting to stop Putin. So Ukrainians are doing it for all of us. They're dying every hour to keep democracy alive, and they're fighting for the rest of us. So the least we can do is give them all the support that we can. So I very much urge you to please support this cause, as well as whatever other causes you see on to help Ukraine. All right. So let's now talk to something more happy, which is research. And again, you know, you cannot have research in a totalitarian state. So let's enjoy, while we can, the fact that we are in a liberal democracy and we can have open research, and talk about self-supervision and datasets. Okay. And I will start from the beginning when I started graduate school, and this was the pre-dataset era. Okay, I started in 1997, 1998, and back then, the world was very, very different. In papers, we didn't have any numbers, right? There was no tables of numbers. There were just images, and there was even like a joke, about CVPR in the 1990s. If a CVPR paper has a single image, it's a hack, right? They couldn't even, they could only make one result work. If it has two images, it's an algorithm. But if it has three images, it's a framework. It's clearly, absolutely fundamental contribution. And just for the fun of it, I went back and thought about checking out one of the most famous paper from kind of the old computer vision era. The candy edge detection paper. Okay, lots of citations, super famous, definitely a framework. So how many images did it have? There's one image, there's second image, there's third image. So obviously it's a framework. Okay, but then things started to slowly change in around 2000s, and I was there for part of this change. This was one of the things that started to happen in computer vision. People realized that, we really need to measure how well we are doing. And so one of the first data sets was this data set to measure how well something like edge detection would work. So there was this Berkeley segmentation data set where humans would label edges, and then you could actually evaluate how good is candy edge detection, and how good are the new ones. And they can even say, oh, look, but here is this point where the humans are, so we can tell how far we are from humans. So suddenly we could reason about how well we are doing. Okay, and that was kind of the beginning of what I call the dataset era. Okay, and back in grad school, my advisor Jitendra Malik made us all learn this Lord Kelvin quote, and indeed, data sets have brought us many breakthroughs. I'm sure even people outside of computer vision know of the SIF descriptor by David Lowe. Probably most of you don't know, though, that when SIF descriptor came out, it was an ICCV 99 paper. It was a humble little poster at the very corner of the room. I think I was the only one at that poster. It was very, very, very sparsely attended, and it didn't make a splash at all. What made a splash was a paper by Christian Mikolajczyk and Cordelia Schmid in CVPR 03, where they actually had a data set, and they had a comparison of all the feature detectors out there, and suddenly it turned out that SIFT was just beating everybody in a very strong way. Okay, and that's when SIFT became SIFT. It became SIFT because a data set validation told us it was very good. The same thing happened with the formal part models, thanks to the Pascal VFC data set. And of course, most famously, the same thing happened to CovNets, thanks to the ImageNet and the Pascal data sets. Okay, so data sets have brought us absolutely real breakthroughs. Okay, but in the beginning, data sets were really used for evaluation. They were used to really evaluate how well you're doing. Okay, and then at some point, we realized, wait a minute, we have all these beautiful data sets for evaluation, for testing. Why don't we also just train on them? And that's where things started to go a little bit bad. Because if you look at this old example that we did with Antonio Torralba, you train a detector on, say, cars on one data set, let's say MSRC, and then you run it on other data sets, and you realize that for a lot of them, you don't actually get the cars. It doesn't actually detect cars. So it turned out that there is this fundamental thing that basically all data sets have. They're all biased in a way that often somehow imperceptible, but the cars of ImageNet and the cars of Pascal and the cars of LabelMe, they're actually quite different cars. So when you're training a system to detect cars using ImageNet, you're not actually training to detect cars. You're trying to detect ImageNet cars, which is a subset, which is actually quite small compared to all of the cars that are out there. Okay, and it's not really kind of, you don't think of it as a domain shift. It's not a domain shift. The cars are cars in the world. Okay, it's just bad sampling. All data sets are sampling from the world, and they're not sampling IID, right? It's very, very hard to sample IID. And so this is an absolutely fundamental problem. And coupled with the fact that classifiers just love to cheat, it becomes a real issue. So here is an example of that I like. So here is an example from ImageNet. So you have an image and you give it to a network. It says, oh, it's a collie. And then you apply one of those texture synthesis things like the Gaddis texture synthesis, basically scramble the image around to basically make a texture out of it. You give it to the network and it's unperturbed. It continues to think it's collie, and this is collie, and this is collie. So basically, the network does not really need to think about finding object versus background, finding occlusions or segmentation or anything. It doesn't need to find collie. Just basically just enough to show some collie texture. Okay, so it's happy to, instead of doing object recognition, it's basically doing texture recognition, right? Why? Well, because you only have 1,000 labels and it's not such a hard task, right? And things can get worse if you go to something like video. For example, here is a input video. Somebody is opening the fridge door, and then in video recognition, the task is to basically say what's the class label? Is it picking up cup? No. Is it slicing bread? No. Is it opening fridge? Yes. Okay. And we can do really, really well in this task. 99% performance. It's absolutely fantastic. But if you look at what it's doing, it actually doesn't need to look at the whole video. It actually doesn't even need to look at the most of the frames. It's only really needs to look at this one frame of this open fridge texture to make this decision. Okay? So it doesn't need to track the hand. It doesn't need to know about the fridge door. None of this. Okay? It's just basically looking at this. Oh, it's definitely opening fridge. Okay? So clearly it's cheating. Okay? And maybe 5 years ago, I was thinking, well, we just need to somehow give it more data and it will stop this bias. And now I'm realizing I don't think that this bias will ever go away. I think the fact is that the data sets, just by virtue of them being fixed sized, finite, there will always be a way to cheat, to find some shortcut and not really do the task, right? Because really what ends up happening and what works the best is just learning, memorizing these XY pairs. It's kind of like, I like to compare this to college. You some boring class, your whole semester you skipped class, you didn't come to the lectures, and then the night before the final exam, what do? Well, you get all the exams and you do cramming, right? You take question answer, and you just memorize it. And as we all know, cramming totally works, right? You do well on the exam, but you don't actually learn the material. And so what I'm worried about is that we are raising a generation of algorithms that they are very good at cramming for the test set, but they don't really know the material. Okay. And okay, you can ask, is the memorization so bad, really? And actually, it's not that bad. In fact, imagine there was another Earth, and if in that Earth, instead of evolving a brain, we would evolve a lookup table, okay, a memory, and it would be really, really cool because the children could inherit their parents' memory. Like it's like just we would know so much stuff, and we know this is a good thing because Clover and Hart told us that k-nearest neighbors is the best thing you can do. It converges to Bayes' risk, right? It's really, really great as n goes to infinity. It's absolutely fantastic. so this kind of memorizer is actually should be doing pretty well, except that's not what happened on Earth, right? On Earth, we did not evolve a lookup table. We involved a brain, okay, which is worse than nearest neighbors. But why did we evolve a brain? And my argument is that we evolved the brain because we live in a changing world. Our world is not static. Memorization is great if you live in a static world. If your world is always changing, some of the stuff you memorize is no longer relevant. So what you need is you need a brain to generalize to new things that haven't happened before that will happen in this changing world. So I think generalization is absolutely fundamental to trying to figure out how do we get computers to have intelligence. So what can we do? How can we get rid of this kind of memorization bias? So one way is basically kind of, I call it the Berkeley Montessori school kind of, 60s hippie things. Okay, get rid of all tests. Okay, don't test the computers on anything. Don't have any objective. No objective, no way to cheat. Great. Now it sounds a little bit crazy, but actually this is not that crazy. And the idea of intrinsic motivation or curiosity coming from psychology, developmental psychology, tells us that actually it's a pretty reasonable way to go. Another thing we can do is kind of the other extreme, and this is kind of like my Soviet high school, relentless daily homework. So instead of a final exam at the very end, once a semester, no, it's continual online learning, 7 days a week homework. It's brutal stuff. You get tested every single day, okay? So now instead of a fixed data set, you have like a continual stream of data. You're being tested all the time, every single day. Now, of course, it's hard to get humans to label so much data, but lucky for us, we have self-supervision. So the hope is we can actually get those labels automatically, okay? So why is not having a fixed data set a reasonable thing? Well, one is a real world motivation, right? Biological agents really never see the same data twice, ever, right? You see a new piece of data. First, it acts as test data, and then, assuming that you survive, let's say the test data is an encounter with a lion or a tiger, if you survive, then you can use the data to train so that the next time you do better. But the next time it's going to be a different tiger in a different situation. So it never repeats, okay? And I worry that repeating the same sample over and over and over again actually encourages memorization and discourages generalization. And really, in the olden days when data was scarce because labels were hard to get, that maybe made sense. But now when we use self-supervised learning, I don't see any excuse to use multiple epochs. Really, if we have infinite data, we have infinite labels. We should never ever see the same piece of data twice. Some people say, wait, what about consistent evaluation? Surely you need, to get consistent, this fixed data set for evaluation. And I'm not sure this is such a clear thing, because yes, it's nice to have a consistent evaluation, single data set, but all the other areas of science can live without this. Healthcare, polling, stock market. Nowhere else do they have the luxury of having a fixed data set. With vaccines, for example, right? They had to keep getting new people and new data. It's okay. It's harder, but our statisticians friends have figured everything out for us. Error bars, p-values, all this good stuff. We can use all of that stuff and deal with the fact that we don't have a consistent, we don't have the same data set to value. It's fine. Everybody else can do it. We can do it as well. Okay. So basically, the argument here, it's instead of having kind of just this fixed training set, or slightly better, like a training set and a val set, we can basically think of it as a kind of a continual data stream where every new sample is first a validation set, and then it becomes part of the training set, and you just move on forever and ever. Okay. What about catastrophic forgetting? Well, maybe catastrophic forgetting shouldn't be that, we shouldn't worry about it so much, because, you know, if you don't want to forget all data, then it's probably that actually your distribution is stationary. Probably your world is not changing, in which case it's just that your sampling is not IID, in which case, you know, you just get yourself a big buffer and make your sampling IID, and off you go. And if your distribution is actually shifting, well, then actually you probably don't want to remember the old data, because the old data is going to be invalid now. And so maybe it's not so bad. Okay. And so this is basically the kind of the motivation for some of the work that we have been doing in my lab. We call it test time training. And it's essentially an attempt to operationalize this continual learning on an infinite, smoothly changing data stream, using self-supervision to very quickly adapt to your test data. Okay. And we already applied it in the case of RL with our curiosity work. I just kind of remind you very quickly, it's kind of old, but still kind of cool. And basically the idea here is that we have an agent, and the agent has an observation, which is a Mario Brothers game, and it has action, you know, the keyboard, the joystick, whatever. But it doesn't have anything else. It doesn't have access to the score. There is no objective. Okay. There is nothing to optimize here. It's just, its objective is basically to be curious, which is basically to predict the future. Okay. So basically the goal of the agent is to, you know, press the buttons that try to predict what's going to happen to the pixels. Okay. And so it's, before it presses the button, it basically makes a prediction first, and then it see what happens, whether prediction is correct or not. Okay. So here it's correct, and here it's not correct. And here it's also not correct, right? And so whenever it's not correct, that's actually when it becomes more curious. So curiosity is basically failure to predict in our formulation. And then we have this kind of like a adversarial kind of system where we train a model, it tries to predict the consequences of its actions, and then if the prediction is bad, it increases its curiosity, which makes it want to predict farther in this space. And if its prediction is correct, then it says, okay, I'm getting bored, I need to move on and predict somewhere else. Okay. So this is kind of this battle between the predictor and the curiosity. And the prediction is basically just, you know, you just predict the, you know, given the action and the state, you predict the next state. Okay. And basically just applying this very simple trick without any external reward shows us that we basically, okay, in the beginning nothing happens, but after some training with this curiosity model, you basically show that Mario starts playing the game. It basically things like wanting to stay alive and wanting to move on kind of emerge automatically just because it's more curious to go and see the future rather than to get killed. Okay. And so a lot of cool things just emerge, like jumping enemies, killing enemies, staying alive. Staying alive is an emergent property. And, you know, here's a cute thing we did. We basically made curiosity-driven agents play Pong, and they play Pong exactly the same way that I played ping pong, right? It's like the scores are not really the thing. Like the scores are kind of low. Like the thing is about, you know, me playing ping pong is just keeping the ball in the air, because, you know, making a rally is more fun and more curious than winning. And this is basically what it's trying to do here, which is kind of neat. Okay, but this is basically, you know, it only works in simulation and it relies on restarts, and it's you know, it's in this RL world, which is kind of nicely suited to this online processing. But what about something that's outside the RL world, something that's, you know, my field really is computer vision. So can we apply the same kind of ideas to computer vision? And here, one of my main inspiration is this paper from Asaf Socher and Michal Arani and friends, is this beautiful paper that says, you know what, one sample might not be such a bad way to train a model. So here what their task here is super resolution. And so the classic way to do super resolution is you have a whole bunch of training images, you make them half size, and then you train a model to basically upsample a whole bunch of your images. And then at test time, you have a small image, and then you use that model to upsample it, right? That's kind of the standard thing. What they did is this completely crazy thing, okay? They don't have a data set. They only have this one input image. And what do they do at test time? They take that image, they make it even smaller, they train a tiny little model to upsample this really small image back to the test image, okay? And once that model is trained, they apply that model to the test image itself to upsample it again. And magically, so here is an input image. Here's what happens if you upsample it using kind of standard, the large data set, deep learning. And this is what happens if you apply it using a model trained on this image itself only. Again, lots of data, one image. Why is it working? Well, it's working because this model is just perfectly made for this image. It's overfitting to this one image, but it's exactly the right image that we want. So it's a really neat idea. There was other papers, for example, Eric Learned Miller had an old paper that says we can improve our face detection. If we have detected one face in an image, we can actually fine tune our detector a little bit to detect other faces in this same image, because they probably have the same, illumination and other, camera models and stuff like this. Okay. And so that basically was the inspiration for us to do the test time training story, which is basically say, okay, your standard error is, you're given a new sample X in the distribution queue, and you need to see how well you do. But if your distribution queue is different, if domain has shifted, then what can you do? Well, what actually is that this sample X can actually give us a little hint about what that new distribution queue is, right? Just the data in the sample X actually gives us a little bit of information about what is this new distribution. And so what we can do is we could try to update our model a little bit, given that we know that we are processing our sample X at test time, okay? So now we don't have a fixed model anymore, but our model adapts at test time, once we already know what is the input sample that we have to deal with, okay? Now you say, wait a minute, this is crazy. How can you fine tune your model if you don't have the label, right? You only have the X, you don't have the Y. Aha, that's where we are going to use self-supervised learning, okay? So we might not need the label after all. So here is a very simple kind of a toy scenario. So let's say we want to do image recognition, scene object recognition. So we have an image here, and we want to know that it's a bird. Okay, so this is our main task, and we can train on this main task at training time. And then at the same time, we can have another head, and the other head can do some self-supervised task. In this particular case, the self-supervised task is basically predicting the orientation of the image. One of 4 orientations. Okay, and we train both of them together. Okay, now test time comes. Of course, you don't have the label anymore because it's a test sample. We've never seen this before, but we can still do our our self-supervised task, because that we can create ourselves. So the idea is that you do a little bit of fine-tuning on the self-supervised task before you actually go ahead and output the answer for the main task. Okay, so that's basically the idea. It's very, very simple, and it seems to be working. So here is an example from ImageNet, and it's an elephant, but it's a very unusual picture of the elephant. So the standard model basically thinks it's a dog more than it's an elephant. But then just doing a few gradient steps on our self-supervised task shows you that, oh, no, actually, it's unlikely to be a dog. It's more likely to be an elephant. So you can see that it's doing something reasonable here, okay? And we can do well on some silly ImageNet-C data set or whatever, okay? But there is a big hidden assumption here. And the assumption is this, that those tasks, the main task and the self-supervised task, are well aligned, that whatever features you learn here from the self-supervised tasks would actually be beneficial to your main task. And that's not clear that that's actually going to happen, especially with this rotation prediction task. Sometimes the rotation prediction is very simple, right? If you have a horizon in your image, then the rotation prediction is very simple to do. But sometimes it's basically impossible to do. If you're looking at an object that's basically rotationally invariant, then it's impossible to do this task, okay? And if you're not doing well on this task, then there is no chance that this is going to get updated, okay? And so in this coming NeurIPS, we have a follow-up to our previous story where we realize that all we need to do is we need to get a more general self-supervised task. And we are big fans of masked out encoders, and that's what we are going to be using, okay? Masked out encoders, to give a little bit of a background, this is actually something that we did 5 years ago. We called it context encoders, but we didn't have enough parameters, so it didn't work so well. But with transformers, it works fantastically well, and it's basically a task that's a very general task, right? So the task is take an image, drop out some parts of it, and then reconstruct back the image. And the nice thing about it is that it has a very nice dynamic range, right? The task, you can never solve it perfectly. It's hard enough that there's always going to be something to learn. But even in the worst case, you are able to do a little bit of something. So again, it's not impossible. It has this nice property that it's not super hard and not super easy. It's right there in the regime where we want. Okay, and so we thought, perfect. So basically, the idea is we're going to start by training a masked out encoder, then we are going to freeze it, and then we are going to add to it another head, which is going to be the task that we actually want to do. Let's say, classification, okay? And then we train for that task. We fine tune for that task as well, okay? So this is all the training time. Now, test time comes, have a new image. Okay, what do we do? Well, the first thing we do is we run it through our masked out encoder, and we basically want to try to make it work better as a masked out encoder. This is a self-supervised task. We know exactly what we want to get. The output is exactly the input. So we just basically use a few gradient steps of fine-tuning to make this better, okay? After we have done that, then finally we allow it to do inference on the main task and produce our result, okay? So again, very, very simple story. And what we are seeing, again, like in the case before, as we go on with our fine-tuning, and here we are using a few more, about 500 steps, we get the reconstruction loss gets lower and lower, and the class accuracy gets higher and higher, okay? And what's kind of amazing, to me at least, is what I would expect that at some point it would peak and it would start going down, okay? That you fine-tune and it would get better and better, and then it will basically start overfitting and it would start getting worse again. But that does not happen. And I'm not quite sure why. It basically says that overfitting to this test input is actually okay. It doesn't screw things up. I'm not sure I understand why this is happening. I'm not sure my students understand it either, but I think this is a very cool, unexpected kind of result. Okay, and we tried it again on this ImageNet task. actually just adding just using the MAE already gives you a huge boost. And then once we have the test time training MAE, then we can do even better than that. Okay. But now, okay, I talked about this continual data sets, and here we are looking at ImageNet again. So what's up with that? Well, we tried it on a bunch of different larger data sets, but to me, I think more exciting is to try to use this on streams. And what are the best streams in computer vision? Video streams, right? And here the idea is, instead of basically doing a single sample problem, you adapt to one image, and then you throw everything away, adapt to the second image, throw everything away, adapt to the third image. Instead, we can basically just do it in a kind of an online no reset setting, where every new image, every new frame or a video, we adapt to that, okay, and then we just keep going, okay. And maybe we reset once in a blue moon just to make sure it doesn't go into crazy land. But basically, we keep what we learn, and we keep updating that. Okay. And so we are currently working on this with basically test time training on video streams. And here are some preliminary results on things like segmentation. We can also do this kind of thing, and you can see that it's getting better. It's still not quite there, but I believe it's getting better. Here is an example for polarization, and it also seems like it's doing better. Okay. We also applied this kind of method back to the robotic setting. So here it's kind of a sim to real kind of setting. So we train a robot in simulation with reinforcement learning and a self-supervised task. And then, of course, in real case, moving it to a real world, you cannot do RL anymore. It's too expensive to do RL. But you can still do your self-supervised task, okay? And basically, we can adapt to the real world using the same kind of test time training idea. And here is an example. This is a robot in simulation, and this is a real world. And we also made it a little bit of like a discotheque setting to make it harder. And it's able to still deal with the task at hand. Okay. So this is all kind of nice and cool way to adapt to this unknown future with a little bit of fine tuning. But what if you want to just do it at inference time? No fine tuning at all. Adapting to the world with no fine tuning. And here we are very jealous of NLP folks, because in NLP, you guys can already do this. Like, this is basically what prompting in GPT-3 is, right? So you train on a self-supervised task, doesn't know anything about translating French to English, and then at test time, you give it a prompt, and boom, it figures out, oh, you want me to translate from French to English? I will do it for you. Okay. Very cool, right? And can we do this for visual data, though? Can we adapt this idea of prompting to the visual data? And here, I remembered that actually we have something like this. Back 20 years ago, we had the idea, which was called image analogies by Aaron Hertzman, SIGGRAPH 2001, which is kind of prompting in the visual domain, right? And those of you who took, the standardized tests should remember, right? It's basically A is to A prime as B is to 1, right? Except it's on images, okay? And so here we can basically set our task with these two images, and then we can ask it for the next things, the resulting image, right? And those tasks could be basically anything, right? All you need is you just need a pair of images, okay? No constraints, okay? So this is our task. This is what we want to do. Now, how are we going to do this? And here I would like my audience to take a moment to think about the stupidest, simplest thing you can think about to solve this task. Okay? Just the simplest thing you can think of it. And I bet that the solution that my students came up with is actually going to be even simpler than that. Okay, ready? Everybody has a theory? Okay, so here is what they actually propose to do. Okay, and this is totally, I have no hand in this at all. This is totally them. I'm still kind of amazed that it works. Okay, what they did is basically take the three images of the analogy, put them in the same big image with the desired thing as a whole in this image. Okay, and now they just applied an in-painting model, a hole-filling model, for example, the MAE, to fill in this hole. That's all. And magically, it's actually doing something reasonable a lot of the time. Okay? It's as simple as that. It's really, really simple. Okay? So, and it does it for like a range of tasks. Polarization, segmentation, font style transfer. Sorry about the PowerPoint glitch. Hole filling. Well, of course, we can like edge detection, style transfer. Now, of course, training data is very important, and you try it on ImageNet data, it's not going to work. Okay, so there is a trick, and the trick they used, it's kind of a hilarious trick. They basically scraped 20 years worth of computer vision papers from archive, and they scraped all of the figures from all of the papers, and they used those figures to train the MAE model. Okay, now there was no parsing of figures, nothing fancy. It was basically just random crops of computer vision figures from archive. Okay, but that was enough to essentially probably learn this kind of grid-like structure that probably taught the algorithm about essentially analogies, right? Because in our papers we show like the before and after, and the baseline and our algorithm, right? These are all kind of very much kind of analogy inducing things, and we always have multiple examples of the same algorithm. So basically, as it turns out that computer vision papers are very good things if you want to learn about analogies. Okay, and so basically the model is essentially is MAE, but to make the pictures look a little bit better, there is a VQ GAN there to basically to have a to output VQ tokens, so it makes it look better. And the results are, I mean, they're not like amazing. It's not going to beat any records on any of the tasks, but it does something from just a single example. Okay. And some of those tasks are kind of classic computer vision tasks, but some of these tasks nobody has ever tried before. For example, here is kind of synthetic tasks. So here, first we instead of one example, we can give it two examples. That's not a problem. Just make the image bigger, right? And it's basically kind of figuring itself out, right? Here, the same thing. It's kind of figured itself out, right? This has never been in any vision paper. It's kind of seems to be doing the right thing approximately. Notice that it's not quite proper analogy, because an analogy has a directionality. It's like, A to A prime as B is to what? Here, in fact, we are kind of symmetric, right? The analogy can go vertical or horizontal. So the question is, does it matter? Well, it definitely gives you somewhat different results, but it's similar, and you can see from the activations kind of that it's adapting and doing the right thing. And I think that's because in vision papers, some people show the results as columns and other people show it as rows, and it basically learned both ways. We also tried different types of prompts, kind of just different colors. So, inverting the color of the mask, for example, seems to work okay. Again, a little bit different, but still works okay. Different colors seems to be doing okay. Instead of segmentations, we tried boundaries. Now that makes it harder. There's smaller signal. When we really defeated it is when we used textured labels instead of unicolor, and then it completely goes berserk. So it's not magic, but it's surprisingly robust. Ways we can improve performance. Well, of course we can give it more task examples instead of one. To have more examples in a support set. But more so surprisingly to me is, while using something like ImageNet data did not work by itself, adding more data from, say, ImageNet, in addition to the data that we had, totally improved performance. So it seems like you need the good data, but you also just need data. And so really what we want to do is we want to have both good data and just lots of data, and they don't have to be the same thing. Okay. And so here is some more examples for you. And of course, it's again, as I said, it's not magic. Sometimes there's basically task ambiguity when you're looking at something like this. Do you mean colorize this image, or do you mean turn everything pink? Well, it decided that it means turn everything pink. Here, it's also not clear what is it that we want to do. It only works on, it assumes things are aligned. So it basically kind of like image-to-image translation task. Things that are not aligned, it really doesn't know what to do. Okay, and again, there is no magic. It's not going to do semantics for you. It's yeah. So why does it even work? Well, you need the right data, of course, but I don't think it explains all the surprising generalization it's able to do. So I think that these large impinting models, they really do capture something very interesting, some kind of a long-range, high-dimensional correlations and symmetries that are actually kind of the useful bit of analogy understanding. So I think there is really something magical there. Plus, I think it also suggests that some of our kind of computer vision and pattern recognition tasks are maybe quite a bit simpler than we think, and we should really up our game and try to do harder things. Okay, so in conclusion, training data sets were very useful to establish computer vision as a real science, but it might be that this focus on this static data sets is might be hurting us now. And maybe we want to think beyond this fixed train and test split and really think about other regimes of dealing with our data, either as a streaming or as a zero shot, of some other way to really deal with our world. And with that, thank you very much, and Slava Ukraini.
For this great presentation. Yeah, I think we can go to the questions.
Thanks a lot, Alexei. Thank you very much. So I'll start with this. So you started with a pre-dataset era. Then you said, then we moved to the dataset era. So my question is, where are we now, and what is next? Are we going to the Are we now in the self-supervised learning era? Are we moving to the reinforcement learning era?
So yeah, so I think that we are entering the post-dataset era. I think that we are going to be in a regime where this is going to be great for our hard disks. I think we will stop storing data on hard disks. I think we will just open up a socket and just download things from the internet or from whatever, compute it online, and go on from there. That I think we will not need to store things. That's at least my hope. And because a fixed data set it could never be large enough that, for what we need. And it's going to be stale as soon as you download it. It's already stale, right? Because the world is moving on, the world is changing. And so I do believe, like, my dream is that, my students would test their vision algorithms by just, plugging into the, HBO TV broadcast and just running their algorithms, training them directly on television broadcasts, and testing them also on them, for example, right? Now, I think we're still kind of far from that dream, but that's my hope.
Do you have any thoughts on what is the role of multimodality and large-scale training, which is so popular these days?
Yeah, no, multimodality is, I think, absolutely very crucial, and for in computer vision, for example, the natural friend for us would be audio, and in fact, we have done some work on combining video and audio. This is a very natural thing. But I think actually the biggest benefit from multimodality will come from in robotics, where you can combine vision with proprioception, with sensing. That's, I think, where really a lot of juice will have to come from, because that's a very untapped world. And again, it's something where, in robotics, it's very hard to do data sets, right? In robotics, again, it's the same kind of thing. You need to be out there in the real world and capturing the world. Large scale models are actually going to be a big help here, because you don't need to have a large data set to train a large scale model. You just need to train something for a very long time, right? It does not need to be a data set. It could just be a stream of data that you just continue training. And so I think what we will see is that people will kind of stop training things from scratch. That everything that you train is, maybe you use the model you had from your previous project, and you just hook it up to new data, and you just continue training. And then you hook it up to other data, and you continue training, right? And I think that's where we will get the large scale. So I think the large scale does not have to mean, okay, you have to train on a line data set. You don't have to. I don't think those things are necessarily need to be connected. I think it's just that you should never start over. You just keep training. Just like when we learn about the world, right? We don't zero out things. We still remember the stuff we learned when we were 5-year-old, right? It's just that maybe some of what we learned when we were 5, we realized that was wrong. But that's not an excuse to just completely wipe it out and start from scratch. And I think the same thing is going to happen. We'll be just nursing our little models that will just be learning more and more stuff. And if some of it will turn out to be wrong in the future, that's fine. That's not a problem.
Okay, so let's have a look at a couple of questions we have in the slide in the chat, I guess.
Yeah, so we have one. How to choose the number of steps for fine-tuning, especially given that there's no overfitting?
I think it's in the context of test and training.
Right. So that's what I mentioned, that, I mean, the way that my students chose the number of steps is the smallest number of steps that did the job, right? But so it's kind of a empirical finding. But what they found, which again I'm very surprised about, is that I thought that you could overdo it. Like if you have too many steps, you will overfit. And they did not find this. They tried, they tried fine-tuning for a very long time, and the loss never, like the performance never went down. So it's not actually as critical. The correct number is not as critical as I would have thought. Basically, you can fine-tune for a long time and it's going to be fine. It's just that it's going to take a long time. In my beautiful story where you hook up your model just to a TV broadcast, my hope is that we just fine tune for like one step. At every frame, it's just one step, right? It's really online, right? And I think that could be possible. Okay.
Okay. I guess the next question here is a bit related to this. So I'm a big fan of test and training. I love this idea. I heard you presenting it also several years ago. But the question is, so my understanding is that self-supervised learning is kind of data hungry, right? So you need a lot of samples to train it. And at test time, or the usual test time, we want the model to be able to, let's say, classify one single sample, one single example. So now at test time, with test time training, are you assuming that your test data will be broad? That you will be? Are you assuming that you will have access to a lot of test data to make test time training work? Is it one of the limitations? Maybe?
Well, yeah. I mean, there is a little bit. I agree with you. There is a little bit of this contradiction that test time training needs lots of data, but here we are trying to make it work on a single sample, right? In the reset case, we really want to get something from one piece of one image. Here, I think some of the intuition comes from the Asaf Sosher work I mentioned about the super resolution, where they magically able to train a very good super resolution model from one image. So how is it with self-supervision? So how does it even work? My intuition is that even though it's one image, if you think about it, it actually includes many, many, many different patches within that image. In a sense, if you think about it from the point of view of like visual texture, a single image is like a data set of patches. And I think that MAE is behaving in a somewhat similar way. Even though you're doing MAE for a single image, because you have lots of different holes that you're trying to fill, it kind of acts as a data set.
Mm-hmm. That's cool.
And so I think that's why we actually there's and you can also think about it in terms of how much supervision you're getting. Well, in MAE, the amount of supervision you're getting is basically as much as there are pixels, or like half the number of pixels in an image, which is hundreds of thousands of numbers, right? So that's a lot of supervision. So I think that's kind of an argument that a single image actually does contain a lot of training data.
Yeah, that's cool. That reminds me of some paper from a couple of years ago about training on a single image, but that image was very rich. So.
That's right. That's right. Yeah, the same kind of argument. Yeah.
Yeah. Another question is from Alex: is it the time to ban ImageNet? Oh, sorry. Is it the time to ban ImageNet at all in CBPR, ICCP?
Well, as you probably noticed, I am a big fan of liberalism, and the liberal philosophy believes in not banning anything ever. So I'm against banning ImageNet, but I'm certainly hope that we will move on from ImageNet, and I think that's already happening. I think ImageNet was absolutely essential. It was very critical. This is what gave us deep learning, really. Like the deep learning took off only after it was proven that it was doing well on ImageNet. But I think we are ready to move on, and so I'm pushing at least my students to try things other than ImageNet. But I think that this will happen. I think this is a natural process. I'm just trying to slowly speed it up. Yeah.
Okay, so let's not ban ImageNet for now. So another question also from Alex: what is the computational cost of test time training? Is it scalable?
I mean, it's not as good as just inference, of course. But again, like the computer, the laptop that I'm sitting in front of is maybe at least 1,000 times more powerful than the workstation that I used to do all of my research, in grad school. But am I doing much more with it now? I don't think so. I'm just doing, Skype and browsing the web, right? Or whatever, Zoom. So I think actually there is a lot of spare capacity at test time that could be used, especially if we do it in this kind of an online situation where we're doing test time training on every frame of a video. Then every frame only needs like maybe one backward pass, right? Like one step of SGD might be enough if you do it every time. So yes, it's more expensive than just inference, but I'm hoping that it's not going to be a huge thing.
Maybe one quick question first is, did you try like with the analogy pictures? Did you also try diagonal? Just out of curiosity, there was like the columns and the rows, and it both worked. Did you also try to do diagonal ones?
Interesting. No, we haven't actually. At least I don't think we have. But the code's online, and you guys can just try it. Yeah, I mean it's fun to play with. Sometimes it totally fails, and then sometimes it does surprisingly well, and it's often hard to figure out, like hard to predict. But yeah, I don't know. It would be interesting to see what happens. Yeah.
And just follow up, do you know why it's sometimes doing so well and sometimes not so well, in the sense of, is like, yeah, is there any...
it's hard. Yeah, I think it's basically if the analogy is easy to estimate from the example, then I think it tends to do very, very well. Okay. So I think it's really I think the magic sauce is it has learned to do analogies, but some analogies are hard and some analogies are easy. And I think for easy analogies, it just does very well. And for hard analogies, then it's maybe it's just impossible to do well from even a single pair. Maybe actually then you actually do need to know something about the task.
Yeah. That makes sense. Okay, cool. Yeah, thank you. And last question also from my side is, how is curiosity working different, or how is it different than just repeating difficult samples during training time? And could you also just say, okay, let's keep repeating samples and having several epochs, but just be selective for difficult
right, but to have difficult samples, you need to have a task, right? True. So in a sense, I mean, curiosity is kind of like that, except our task is not. It's a kind of a meta task. Our task is a prediction task, not the task of winning in Mario Brothers, right? And so, in a sense, that's essentially what it's doing. It's doing this prediction task, and then it basically tries to do better in places where it's not doing well, and then So it's basically kind of that idea of finding hard examples and trying to do them better. But remember that it's not hard examples on the kind of the task that we want to have, because we don't have that. Our only task is this general prediction of the future task, which actually I think is really kind of the most important meta task, even for most biological agents. I think even for humans, our main task is to predict the future. And I think that kind of might explain all the other tasks that we need to do.
Okay, cool. Great. Thank you very much for...
Thank you so much. It's very inspiring, and as usual, you have a lot of great ideas. It would be great to have you around at Mila if you have time on the 8th of December. Just let us know. We'll reserve a ticket for you.
All right. Okay. Well, thank you very much for running this, and it was a pleasure talking to you guys. And let's hope this is going to help somehow. Okay.
Have a
Bye.
good day. Very much. Bye bye.
Thank you.